I'm Tyler Slump.
I'm Daniel Miller.
And I'm Cody Hyman.
And we are Team ThunderBox. The ThunderBox is a high-power motor controller for brushless DC motors in robotics applications. The ThunderBox presentation will first start with a project description, then go into the key engineering requirements for the ThunderBox, how the ThunderBox will work in block diagram format, the special considerations for our design in relation to developing the ThunderBox, and finally, the expected development schedule for ThunderBox. Let's get to it.
The ThunderBox is a high-current, three-phase DC brushless motor driver designed for use in robotics research applications. The customer requires that the motor amplifier is capable of quick changes in torque control. The amplifier must also use advanced commutation methods, such as sinusoidal commutation, to ensure low torque ripple.
We will now go over some of the engineering requirements that cover the ThunderBox controller and driver hardware, as well as the associated software.
The engineering requirements for the driver portion of the ThunderBox are to be able to source 200 amps peak in a transient condition that lasts less than 1 second, and to be able to source 50 amps or 35.4 amps RMS continuously. It will also have a single supply that can range between 30 and 60 volts.
The controller portion of the engineering requirements includes an SPI communication interface to receive motor commands and return system telemetry data, an RS-422 level quadrature plus index incremental encoder input to receive motor velocity feedback, a 0 to 5 volt tolerant 3-channel Hall effect phase sensor input for rotor initialization, an ability to respond to external emergency stop signals within 10 milliseconds of receiving them and shutting the system down, and an under or over voltage driver shutdown notification that detects an over voltage or under voltage condition in the driver and shuts the system down while notifying external systems, all within 10 milliseconds.
To meet the continuing software and firmware needs of our customer, we intend to have a USB programming interface so the customer can configure ThunderBox on the fly with no additional hardware, along with a dynamic telemetry reading system which will respond to inquiry within 1 millisecond so the customer can get whatever data they need on the fly. This will all be implemented with a full set of drivers for the Dynamic Robotics Laboratory Medua board, along with fully documented firmware so the customer can update ThunderBox for whatever needs they might have in the future.
Now we'll talk about each of the parts of the ThunderBox top-level block diagram.
The inverter block describes the circuit that amplifies the signals that are generated by the controller. The amplified signals are in the form of high-current sinusoids that generate motion in the motor. The inverter block also contains Hall effect current transducers that measure the output current waveform. This waveform is converted into a voltage, filtered, and sent back to the controller to complete that current feedback loop. The power supplies block provides power regulation and distribution to all the systems in the ThunderBox. The power supply operates on a single input voltage between 30 volts and 60 volts, and provides ripple filtered power to the inverter as well as regulated DC voltages of 3.3 volts, 5 volts, 6 volts, and 12 volts to the rest of the powered ThunderBox subsystems.
The three-phase brushless DC controller block is one central to our design. This block, centered around a motor control application-specific integrated circuit, handles all low-level motor commutation and control, and generates 6 pulse-width modulation signals to control the high-current MOSFET inverter. The controller receives motor setpoint commands from the host communication interface over a dedicated SPI bus, and also returns telemetry data via an asynchronous serial line. Feedback is also employed in this block. The feedback mechanisms include the use of external Hall effect rotor position sensors for initialization, external quadrature encoders for rotor velocity feedback, as well as 2-phase analog current feedback from the inverter section. During active operation, the controller uses the velocity and current feedback to run its built-in control loops. This is the emergency stop interface block. This block connects local emergency stop input and output lines from the host communication interface to an external emergency stop loop. The external loop uses RS-45 differential signaling and provides a fail-safe means of multiple devices in a system to shut down in the event of a critical system fault. Functionally, when either a local fault is detected or an external emergency stop signal is received, This system will ensure that the motor outputs are disabled and will extend this emergency stop to other devices in the loop. This is the host communication interface block. This system acts as a communication hub between an external high-level controller via SPI and the motor controller and driver on board the ThunderBox using a separate UART and SPI bus. Using a microcontroller, it is capable of processing incoming packets, reading driver temperatures, detecting and signaling system faults, and sending properly formatted motor commands to the motor controller block.
The host communication firmware block contains software to facilitate communication between the host controller and the three-phase brushless-DC controller. The software also incorporates facilities to modify non-volatile motor control parameters via USB. The PC configuration software block consists of software designed to run on a desktop computer to be used for configuring ThunderBox operation parameters. As the ThunderBox may be used with different motors and encoders in different conditions, this block allows end users to write motor and system parameters to the host communication interface. The combined heat spreader and mounting plate block provides the ThunderBox module with both inverter cooling and solid mounting to an external metal chassis. This block couples the MOSFET inverter heat with a low thermal resistance to an external metal surface that acts as a thermal reservoir to keep FET temperature in check.
Next, we'll talk about some of the special design considerations for the ThunderBox project. Firstly, we need to manage high current densities and sensing of very large currents. We also need to consider how to achieve 1 millisecond updates and manage the phase lag of the current feedback loop. The Thunder driver has very high power density. It's capable of sourcing 200 amps at a supply voltage of 60 volts with a device footprint of less than 10 square inches. In order to support this design specification, we need to consider the current densities going through all of the interconnects on the board, as well as the efficiencies of the components in the inverter. We also have difficulty sensing such large currents. Normal resistive current sensing doesn't really work in this condition because of power dissipation. So we've used Hall effect current transducers to measure the current.
To fit into the intended robotics application of our customer, the motor amplifier must respond to commands in 1 millisecond to fit into our customer's 1 kilohertz control loop. This includes both control and telemetry data query commands. Because the volume of data which could be shipped from ThunderBox is large enough that it wouldn't fit into the real-time 1 millisecond window, we're breaking up that data so that non-critical information is only transmitted when the customer requests it specifically.
Another aspect to consider is the controller phase lag that may occur. At high rotational speeds with the brushless DC motor, the current flowing into the phases of the motor may not match that predicted by the controller. This phase mismatch can lead to inefficiencies and poor control of the current and thus the torque of the motor. One solution to this that we will be implementing in our final project is the use of field-oriented control. This is a control scheme that will control the torque-generating currents directly and reduce phase lag considerably, leading to a better control system overall. For the remainder of the project, we hope to follow this schedule. At the end of fall term, we should have a finished prototype of our hardware ready to manufacture. During winter break, we will both order and assemble this prototype hardware and begin integration of the software into the hardware. During winter term, we will be focusing mainly on testing. In the first 2 weeks, we will assemble a motor test bench with test equipment and the ThunderBox module. In weeks 2 to 3 of winter term, we will begin subsystem block tests to test each of the blocks independently. And in weeks 3 to 5, we will integrate all of those blocks and test the full system under full load conditions. Later on in winter term, after our testing is complete, we will make further design revisions based on our testing data and any other customer feedback. Hopefully by spring, we will be able to perform initial delivery of the device to our customer, the Dynamic Robotics Laboratory. After this, we went over some of the primary engineering requirements for the project. Among these were the current and supply voltage we operate with, the quick response time of the control system, and some of the safety factors affecting the project. After this, we went over the systems in a top-level block diagram format. We covered the function of each block and how it interfaces with other blocks and the outside world. Next, we covered the important design considerations that are critical to making the ThunderBox project a success. Among these were solving problems with high power density, the torque feedback accuracy, and quick response time of the system. After this, we finish up by covering our expected schedule for the remainder of this project. Thank you for tuning into this ThunderBox presentation.